time we talked about magnets, what they are, how they produce a magnetic field, and today we are going to talk about how that relates to electricity. So it turns out there is a relationship between magnetic fields and electricity, and we're going to learn 3 rules that relate them and be able to talk about how these apply to everyday situations. We are not going to be applying formulas and be doing calculations, but if you're interested in learning a little bit more about this, you can talk to Mr. Munson or myself. So the first rule is that electric currents produce magnetic fields. So experiments show that an electric current passed through a wire produces a magnetic field around that wire. So that means if you go into the kitchen and you want to make a smoothie and you plug in your blender and turn it on, you get current passing through the wire running between the wall and your blender. That current, the movement of charges, actually produces a magnetic field around the wire. So if the current is running this way in your wire, you get a magnetic field that looks like little rings all the way around your wire, all the way up and down it. And this is what the magnetic field looks like. So remember, with a bar magnet like this, it has a north and a south pole. The magnetic field lines always go in a loop from north to south. In a wire, they go just around and around in little loops. Now, how do you know if the little loops are going clockwise or if they're going counterclockwise, which would be this way? How can you tell? Well, it turns out we use something called the right-hand rule to discover that or figure that out. So what you do is put your right hand up and make sure it's your right hand and not your left, or else you're backwards. So put your right hand up and put your thumb up like you're giving somebody a thumbs up. The thumb is the direction of current in the wire. So you can imagine a wire going up and down right next to your thumb. And the current would be running from your hand up to the tip of your thumb. That's the direction of the current moving. Now, if you were to twist your hand inward, following your fingers, that is the direction of the magnetic field. So you probably all look a little silly right now with your hands up and you're twisting your arm around, but that's exactly how you figure out the direction of the magnetic field. So to see a picture of that, in this picture over here, the current is running from bottom to top, or from the hand up to the top of the thumb. The fingers are curling around in this direction, so that is the direction of the magnetic field. Now, it turns out that because a current produces a magnetic field, that wire can now be manipulated by another magnet. Just like you have 2 bar magnets that repel each other or attract each other, you can bring a magnet next to that current carrying wire and mess around with it. And we can actually see a picture of that here, or a video of this. So in this setup, there's a battery to provide a voltage source, a switch to turn the current on and off, a long wire, which is the orangish thing, and a very strong magnet. And when they turn the potential source on and close the switch, current runs through the wire. That current produces a magnetic field, and that magnetic field then messes or interacts with the magnetic field of the magnet. And just like bar magnets repel and attract, they then apply a force on the wire, which is pretty cool. So you saw in the video that a few times the wire jumped up, and then all of a sudden the wire jumped down. And I don't know if you noticed, but in the video, when the wire jumped down, it's because the switch was turned the other way. So what the guy did in the video is the first 3 times the current was running in one direction. Let's say it was going clockwise around the circuit. The last time, he made the current go in the opposite direction, counterclockwise. And because the current was running in the opposite direction, the force applied to that wire was in the opposite direction as well. This is another right-hand rule that we use, although it's a little more complicated. So in this right-hand hand rule, you put your thumb up like you're giving a thumbs up, and then you point your pointer finger straight out like you're making a little toy gun, and then you put the rest of your fingers perpendicular to that or across your body. So you have your thumb up, pointer finger out, and the rest of your fingers in this way. Your thumb will represent the force on that wire. Which direction will it go, up or down? Your pointer finger represents the current, and the rest of your fingers represent the magnetic field. So in this picture, the current is running this way. The magnetic field is moving this way from north to south. So if you were to fit your right hand rule to this, your pointer finger would be pointing in this direction. The rest of your fingers would be pointing in that direction. And to make that happen, your hand has to be upside down. So your thumb is pointing toward the floor. That is the direction of the force on the wire. The force will be pushed down in that case. In the next picture, the current is reversed, and it's going this way. So you would put your pointer finger in that direction. The rest of your fingers would still be pointing from north to south with this magnetic field, so your thumb ends up pointing up toward the ceiling, and that is when the wire jumps upward. Now, we haven't actually talked about this yet, but this is what defines a magnetic field, the force on this wire. The symbol for a magnetic field is a capital B. So if we were using formulas, or if you just want to express yourself through symbols instead of writing out the word magnetic field, you want to use a capital B. And we measure the strength of the field in Teslas, which is abbreviated capital T. So the first principle tells us that when you run a current through a wire, you get a magnetic field. But how can we reverse that process? Well, the second principle is called an induced EMF, and it pretty much is a reversal of the first principle. So almost 200 years ago, Michael Faraday looked for evidence that a magnetic field would induce an electric current. So he wanted to see if I have a magnetic field and I have a wire, and it's hooked up in a complete loop, can I make current run through that wire just using a magnet? It turns out that when he hooked up his wire to a little meter to see if he had any current, and he just held a magnet in there, nice and steady, nothing happened. He got absolutely no current. But he discovered if he moved the magnet either up or down within this coil, he got a current. And the direction of the current depended on whether he moved the magnet up or down. So this is what we call an induced EMF, or a magnetic induction, that a changing magnetic field can produce a current in a wire. So you need three things to make this happen. You must have a magnetic field. So you need a magnet. If you don't have a magnet or some kind of magnetic field, obviously this isn't gonna work. Two, you must have a path for a circuit in that field. So you can have a loop of wire or whatever, but it needs to be a complete path. It needs to be a complete circuit. If you just have one long string of wire and it's not connected to anything or to itself, that is not a complete loop. You will not get current running through that. And three, there must be relative motion between the wire and the field. That means one or both of these has to be moving. So you can move the wire and hold the magnet still, or you can hold the wire still and move the magnet. But either way, you need some kind of movement to get that changing magnetic field. Now the third principle is just a combination of the first two, and we call it Lenz's law. And it'll take a little while to completely understand, but it's really cool and it has so many applications in our daily lives. So Lenz's law tells us when a conductor is passed through a magnetic field, field creates a current in the conductor. This current, in turn, creates its own magnetic field, which opposes the direction of the original. So what the heck does that mean? Well, let's imagine that we have one of those big, scary magnets, and we have a north and a south pole. It has a magnetic field. If I pass a loop of wire through that magnetic field, and I move it so that there is motion relative to those two things, I will get a current in this wire. Now, the first rule tells us that current produces its own magnetic field. So, then, once there is a current in this wire, it will produce its own magnetic field that moves opposite the first one. So to summarize, when a current is passed through a wire, it creates a magnetic field. When a wire is passed through a magnetic field, it creates a current. And when you have this happening, Lenz's law occurs where the magnet's magnetic field and the induced current's magnetic field oppose each other. Lenz's law. So now where can we apply this? Well, electromagnets are a perfect example of an induced EMF. So a solenoid is a really long coil of wire. We get a wire and we wrap it around itself a lot, several times. And when that happens, you get the magnetic field from the current in this wire to be almost uniform and very strong. So when we pass a current through this wire, we know current produces a magnetic field. So we get our magnetic field, which are the blue lines here. And because it's coiled this way, the magnetic field is very uniform, and you can see you have a whole bunch of magnetic field lines packed together in there, and that means that this field is really strong. Now, if you put a piece of iron inside the solenoid, that magnetic field will manipulate that piece of iron or apply a force to it. And the magnetic field will greatly increase. And these have a lot of practical applications. So for example, this is how a manual doorbell works. You have a power source, and when you close the switch, you get a complete circuit through this wire. Now, if you have current running through the wire, that means you also have a magnetic field around that wire and through it. Because this is a solenoid, your magnetic field will end up looking very uniform and very strong. And it will actually make this iron rod move and hit the bell. And that's how a doorbell works. Now, electric motors take advantage of an induced EMF. So what happens is you have a voltage source here, and that voltage source produces a current. So the current has its own magnetic field associated with it in this wire here. Because there's a magnetic field here, it will interact with this magnetic field, which is going from north to south. And Lenz's law tells us that these two magnetic fields will oppose each other, the one from the magnets and the one from the current in the wire. They'll oppose each other, and that will actually physically make this whole thing turn around. So this is an electric motor. A generator is exactly the opposite. It takes mechanical energy and makes it into electrical energy. So instead of putting a current in to move the middle, you physically move the middle, and that will produce a current. So that's a generator. You just took a motor and you flipped it around. Another example of where you can see these rules is a loudspeaker. A loudspeaker is pretty cool. It uses a magnet that exerts a force on a current carrying wire, and this converts electrical signals into mechanical vibrations. So we're going to talk about sound in a few weeks, and it turns out that sound is nothing but a vibration in the air, which is really cool when you think about it. So that's exactly how a speaker works. A speaker vibrates in a very specific pattern to produce certain sounds that your ears pick up. And it vibrates because we can turn electrical signals into mechanical vibrations. So we have, if you were to look inside a speaker, you would see a cone here, and that's what is actually vibrating to put out the sound. You have magnets in here as well, and those magnets produce a magnetic field, and they go from north to south. Now, when you run a current through these wires, so you've plugged your loudspeaker into the wall and you get a current, the current produces its own magnetic field, which interacts with these magnetic fields and produces a force. So that force is physically what makes the loudspeaker go in and out. So the kinds of signals you send to the wires will change the magnetic field, which will change the way that these two things interact with each other, which changes the force and then the vibration pattern. It's pretty cool. Now, a final example of where you would find these is a microphone. A microphone works by induction. So instead of pumping current in to mess around with, make a magnetic field that interferes with another magnetic field, you actually cause mechanical vibrations using your voice on a membrane in the microphone. And as that moves back and forth, you have a wire right here that's moving relative to a magnetic field. And remember, if you have a wire moving relative to a magnetic field, you're going to produce another magnetic field in the coil. And this will translate your mechanical vibrations into electrical signals that get sent to an amplifier or a recorder or whatever it's hooked up to. So I know we ran through that really, really fast, so make sure to ask questions if you have them. For homework, I want you to answer the following questions, which will hopefully help you process all of this and apply it. And you're going to see some really cool demonstrations with this stuff in class. So your homework questions are, 1. With magnets, we know that likes repel and opposites attract. So how does a compass work? This should seem very familiar to you. And 2, list the 3 principles relating current and magnetic fields and name an example of where this can be seen in real life. Now, if you name an example that I listed in the video, I want you to tell me how it works. You can also look up another example because there are tons out there. But please, if you look something up, cite your source. I personally don't mind if you look stuff up. I don't think Mr. Munson really minds either. But make sure you're not taking that credit for your own. If you don't come up with an example off the top of your head or from this video, you need to cite your source.